Welcome to the deep dive. Today, we're plunging into a world that you might not see every day, but it's absolutely foundational to, well, pretty much everything engineered around us. We're talking about the precise measurement of force.
Yeah, it's fascinating. I mean, think about the huge forces in, say, aerospace, or even their tiny pressures in a medical device. There's this unsung hero doing the work, translating physical force into data we can actually use.
Right, these unsung heroes, load cells. So what exactly are they?
Okay, so fundamentally, they're transducers. That means they convert one form of energy to another, in this case, mechanical force.
Like pushing, pulling, twisting.
Exactly. Tension, compression, shear, torque. They take that physical force and turn it into an electrical signal. And the amazing part is the precision. I mean, really incredible accuracy, sometimes down to fractions of a pound.
Which sounds great, but I guess the challenge is there's no single load cell that does everything perfectly.
Absolutely not. That's the key thing. It's a huge field with loads of different designs. Each one is kind of optimized for specific jobs, specific conditions.
Okay, so our mission today in this deep dive for you listening is to unpack that. We want to look at the main types of load cells, figure out not just what they are, but more importantly, why they're built that way. What problems do they solve?
Exactly. It's about getting you past the basics and into the engineering choices behind them. Why pick one over another? That's crucial.
So let's start with the why. Why are these things literally everywhere? You mentioned aerospace, automotive.
Oh yeah. Aerospace is huge structural tests, component validation, automotive, think crash testing, engine force measurement, braking systems.
The energy sector.
Turbines, pipelines, you name it. Medical devices need them for diagnostics, drug delivery pumps. Industrial automation relies heavily on them.
Even in like regular products, OEM equipment.
Definitely. Anywhere you need reliable, accurate force data, chances are there's a load cell working behind the scenes. It's the linchpin for so much control and safety.
Which brings us to a really important point you touched on, choosing the wrong one. That sounds like it could be bad.
It can be disastrous. Seriously. It's not just about getting slightly inaccurate readings, though that's bad enough. It can lead to equipment failing way too early, or worse, major safety hazards. People could get hurt.
So it's more than just how much force can it handle?
Oh, much more. You absolutely have to think about the environment. Is it boiling hot, freezing cold, damp, vibrating like crazy?
Size constraints too, I imagine.
Yep. And which direction is the force coming from? Is it a steady push or is it dynamic, changing rapidly? All these things dramatically influence the best choice.
Okay, that makes total sense. So let's dive into some specific types. Where should we start? Maybe with a classic.
Good idea. Let's talk about the Pancake load cell, or the registered name, LowProfile. Interface actually created the first one way back in 1969.
Low profile, so they're flat and round.
Exactly, flat circular sensors. They're designed for both tension and compression, and they're known for being incredibly stable and precise. The design is really clever. It's kind of like taking two shear beams and mirroring them end to end in a circle.
Okay, and what does that circular shear beam arrangement achieve?
It gives them fantastic resistance to what engineers call extraneous forces. These are forces you don't want to measure, like side loads or bending moments that aren't perfectly aligned with the main force axis.
So they're better at ignoring noise, essentially, focusing just on the force you care about.
Precisely. That's a huge reason why they are among the most accurate types out there. They filter out the junk, if you will.
Makes sense. So where would you typically see these Pancake or low profile types used? High accuracy stuff?
Definitely. General testing labs, precision measurement setups, analyzing materials, and yeah, critical aerospace component tests. That 1200 standard precision low profile model from Interface, still incredibly popular because it's just so reliable and accurate for those demanding jobs.
Okay, so Pancake for broad precision, but what if you just don't have the space for something flat and round?
Right, good question. That's where S-type load cells often come in. The name gives it away. They're shaped like an S.
So much smaller.
Generally, yes. They're super versatile, very compact, and they also handle both tension and compression, just like the Pancake, but in a tighter package.
Okay, S-shape, compact. Where do these fit in?
You find them tucked inside all sorts of OEM equipment. Packaging machines, maybe some smaller weighing systems, places where space is really at a premium, but you still need good accuracy.
Prove small can still be accurate.
Yeah.
Okay, what about shear beam load cells? What's their specialty?
Shear beams are kind of the workhorses for industrial settings. They're designed with stability and robustness right at the forefront. Compact, but built tough.
Tough enough for factories and things like that.
Exactly. They excel there. Platform scales often use them. Automated manufacturing lines where they might see pretty variable loads, but need to keep performing reliably.
Got it. Industrial workhorse. Now, sometimes you need to measure really small forces very accurately, right?
Yes, absolutely. And for those lower force ranges where you need high sensitivity, bending beam and double bending beam load cells are often the go-to. They're specifically engineered to be very responsive at the lower end of the measurement scale.
Sensitivity is key. So maybe medical devices again? Or delicate testing?
Precisely. Automotive testing, particularly for component testing, uses them. Medical applications where subtle forces matter. And certain compact industrial applications too.
Okay, we've covered small and precise. What about the other end? Massive forces.
Now you're talking about canister or column load cells. These are the heavy hitters. Big, rugged, high-capacity sensors built for really demanding jobs.
How heavy are we talking?
Think truck scales weighing fully loaded semi-trucks. Or the forces involved in huge construction equipment like cranes or excavators.
Wow. Structural testing too, like on bridges.
Definitely. Testing bridges, buildings, large structures. These canister cells are designed to handle those extreme loads and often harsh outdoor conditions.
Right. Now, what about integrating measurement directly into a mechanical setup? Is there something for that?
Yes, rod end load cells are great for that. They're compact, shaped with a threaded rod end, making them easy to screw into existing linkages or assemblies.
So you can put them right in line.
Exactly. They measure tension and compression accurately right within the mechanical path. Super useful for lots of industrial machinery and test rigs.
Okay, getting even smaller now. Load buttons, they sound tiny.
They are. Load button load cells are these miniature powerhouses, designed specifically for applications where space is incredibly tight, where maybe no other type could possibly fit.
Tiny but mighty. Where would you need something that small?
Component testing on small parts, precision manufacturing processes where you need to monitor assembly force, quality control checks on small consumer products maybe.
Amazing. Okay, this next one sounds really interesting. Load pins. What's unique about them?
Load pins are quite ingenious. They're shaped, well, like a pin or a clevis bolt. Their unique feature is that they can directly replace an existing structural pin in an assembly.
Wait, so you pull out a regular pin and put in this measurement pin?
Essentially, yes. Imagine a crane hook held by a large pin. You can replace that standard pin with a load pin, and suddenly you're measuring the force directly through that connection point.
Without redesigning the whole crane hook mechanism.
Exactly. It allows you to integrate force measurement into existing structures, cranes, lifting gear, shackles, pivots with minimal modification. It's incredibly efficient for retrofitting or integration.
That's really clever. Okay, we've covered a lot of types measuring force basically along one direction. What if you need more?
Now we get to the superheroes, as you called them earlier. Multi-axis load cells. These are way more complex. They're designed to measure forces and sometimes torques or moments in multiple directions at the same time.
Like up, down, side to side, forward, back, all at once.
Precisely. 2 axes, 3 axes, like XYZ forces, or even 6 axes, which includes the 3 forces plus the 3 rotational moments or torques around those axes. You get a complete picture of the force vector.
Wow. That sounds like you'd need that for a really complex system.
Absolutely. Advanced robotics is a huge area. Think of a robot hand needing to know force in all directions to grip something delicately. Aerospace systems, wind tunnel testing, sophisticated material testing where you need to understand forces from multiple angles simultaneously. They're essential for that real-time, multi-dimensional data.
Okay, that's an incredible range from tiny buttons to multi-axis superheroes.
Yeah.
So bringing it back to the listener, why is understanding this diversity so important?
Well, it comes down to this. Whether you're building a satellite, designing a car's safety system, or even developing a smart fitness tracker, these components, these load cells, are often the hidden foundation. They provide the crucial, precise data that makes modern engineering actually work. You can't design effectively or safely without measuring accurately.
Right. It enables everything from checking turbine performance to crash testing a car properly to making sure a robot arm moves exactly as intended. We really depend on this hidden tech.
We absolutely do. And for anyone listening who finds this really interesting and wants to go even deeper, there are great resources out there. Interface, for example, has their Force EDU platform with videos, white papers, application notes, really detailed stuff on choosing and using each type.
Good to know. So I guess the big takeaway, the aha moment, is realizing that force measurement isn't just this single, simple thing. It's this incredibly diverse and specialized field. And getting the right load cell for the specific task, it's absolutely critical for making things work safely and accurately.
Couldn't have said it better. It underpins so much of our engineered world.
Okay, so let's leave our listeners with a final thought to chew on.
Yeah, maybe think about this. As you go through your day, just notice the objects around you. Your chair, your car, maybe even appliances like your washing machine. Consider the unseen forces involved in making them work, keeping them safe, making them efficient, and how that hidden layer of precise measurement, often thanks to technologies like load cells, makes it all possible.
How might knowing that change how you look at the engineered world around you? Something to think about.